a lighter version of the next segment, which we're going to talk about, which is the GANs in general. The GANs have a lot of utility for us in a lot of different spaces. I also want to discuss some of the things that we might be tempted to do with GANs that may not necessarily be the best way to utilize them. They do have a lot of utility, and they have utility from a research perspective, right? Or at least the way in which we work with imaging data. But we'll talk about that in a little bit, but I want to mention this idea again of how the variational autoencoder effectively works is that the encoder and decoder cycle operations work almost identically to the original framework of the autoencoder space. The difference between a variational autoencoder framework is that it's going to assume a Gaussian distribution, right? The normal distribution characteristic from the spread or the variance characteristics of the sample space. As a result of projecting the distributional characteristics of sample class characteristics inside of that latent space, right, the embedded space, the compressed version, we are able to create a separation, so it's sort of a stratification of those elements in the embedded space that are most highly correlated to the labeled output system. Now, you do need at least some level of labeled information in order to be able to inform the distributional characteristics of the variational autoencoder space, right? It's not going to operate in an entirely unlabeled and sort of unsupervised fashion like we were describing with the autoencoder framework. So the autoencoder in general is able to operate unsupervised because it is just looking to replicate on the output side the input value. Variational autoencoder adds in this level, an additional sort of degree of operational verification by including the distributional representation of the means within the class characteristics and the standard deviation of those distributions. So this informs the encoder's distribution into the latent space such that it is going to make effectively a set of boundaries inside the latent space that describe where the sort of classes and class characterizations, the overlap between those class elements, reside. Previously, if we were looking at the idea of creating an attempt at creating an autoencoder that could reproduce the image of a number, we could look at trying to figure out a way to take the original number input vector, right? Then condense it down to the minimum representation space that that number information could fit in. Now this isn't convolutional network, this is going back to the fully connected idea, right? So I take the vectorized version of the original number image, and then I feed it through the system, condense it down. What we should get in the latent space is what? Effectively, all of the extra stuff that is not necessary in order to describe that number has been taken out. That area is the minimum space in which you can crunch it down into without losing any of its unique descriptive characteristics. When I re-expand that again, I should be able to recreate that number, the original number, in the space. Now, one of the problems with this is we would like to be able to have a system that can generalize to create a type of a representation. Right? One of the examples we had was like the number 3. So we take it in and we train the system with all the numbers. The system learns how to create the latent space and the compression into the latent space that generally preserves the features necessary to pack a 28 by 28 image or 64 by 64 image into some dimensionality less vector, let's say 128-bit vector, right? That vector stored in the center is, as I said previously, compressed. But the weighting characteristics do not differentiate based upon which number was being stored, which number was moving through the system at that time. So it generalizes to the concept of storing a number, not to the concept of storing the number 1, the number 2, number 3, etc. Variational autoencoder space adds the additional labeling characteristic to tell you what the appropriate classification characteristics are of that number, such that the latent space storage of the number features correspond to a specific set of distributional mechanics, such that even though I could take the latent space and attempt to classify the latent space into 1 of 10 digits, right? That would be a feature extraction process. I would have accomplished extracting the minimum set of necessary features. But what am I going to have to hook up to that latent space? When I detach the decoder framework, which is sort of the expansion back to the original size value, I'm going to have to hook up some form of fully connected layers out of the internal latent space into another fully connected learning layer to take those features and learn combinations of features, right? And then have some output dimensionality. In this case, we would say it was a number classifier, 10 outputs. That'd be probably softmax classed in order to be able to get, the likelihood of belonging in class space. I'm then going to train the fully connected layers, but what am I not going to do? I don't need to train the autoencoder. The autoencoder has already arrived at telling me that it figured out the best representation of number compression, right, of feature preserving operations to get the best out of what's being put in a generalized sense. If I switch over to the variational standpoint, right, once I have encoded that framework, I could then take that network, flip it on its head. I could select the input from the train network and say, I want you to give me a 3. And then I could back propagate, I could reverse the expansion process, right? Effectively reinflate the thing I took the air out of. And I should then be able to take that vector, reorient it, and have a picture of the number 3. The problem is that whenever I don't differentiate which particular class the sample was a member of, it doesn't really encode that information. It's not really concerning itself with storing the information relative to the class distributional mechanics. So this idea of providing it with the additional information that relates to the transformation into the latent space of how that class distributes both the mean of that class and the standard deviation actually allows us to have a overlapping set of Gaussian spaces that describe this is class 1, type 1 samples. These overlap with type 2 samples. And the features that are associated with that particular sample type in the latent space are going to be distributed within the latent space in a specific way. The decoder then, right, can accomplish the same purpose that we originally said that the classification output and then flipped version of the model would be able to describe, such that it is going to take latent space vector Z that has been regularized based upon the normal distribution inside the latent space and do what? Reverse the transformation process utilizing the understanding of the original transform. How it was compressed, it expands it in the same way that it was compressed. The difference between the capacity of the variational autoencoder is that it captures the variation, okay? It captures what elements are unique to the class such that those particular items are preserved in the output. So the generative output from the VAE is going to be something much closer to the original input space, whereas if you're training with a standard autoencoder, you might be able to train it to approximate a face, right? But you wouldn't necessarily have it approximating the face of an individual. It wouldn't be a new sample of a facial image that is designed to sort of look like that person. That's the notion of keeping track of the individual characteristics of that person and then creating a utility, descriptive utility that says not only how are the features present and integrated in the system, but then in the encoder step, I'm going to remember the characteristics of that individual person or that sort of latent space representation, and I'm also going to utilize those elements in the reconstruction space. This allows us to be able to both encode something relative to the uniqueness of its distribution, as well as to use the uniqueness of its distribution to reconstruct a new sample that fits within that particular type of distribution. All right, this is the old way in which we did it more frequently, but GANs, as we discussed previously, are the new wave, all right? GANs are probably going to be one of the two more up-to-date things we're going to discuss. Most structures that you come across in the, I guess some of the more high-end sort of data manipulation, data augmentation spaces are going to use some form of GAN relationships, and we'll talk about how they do so. But there are a couple of really neat tools that we've been able to accomplish with these that have started to actually hit retail markets, right? Some of these tools are not just confined to the research space, right? And as many of the other things we talked about, right? Variational autoencoders, probably not huge market application for them at the moment. They do get used in some research-based applications, but most of the things we're going to see that are going to have that had relatively high utility are going to come from the GAN space. So we talked about this previously, that I take a prior understanding, something related to the distributional mechanics of a data set. So I learned the general concepts around how this particular data is generally distributed. I'm not learning unique, specific characterizations of that particular data space at the moment. I'm just trying to get a general feel of the transformations of the data in the network space. Once I get a general feel of that, once I see how the distribution is allocated, means and standard deviations for each of the major classes that the particular data space is made up of, I then have this transform network, which we'll call GZ, right? That is the generator form. And the generator form will then attempt to create a new sample that fits within this distribution, right? It says, if you guys are familiar with classical music, right? It's theme and variation, right? They start off with a little motif, and then they just kind of try every different thing they can do with it. This is kind of the idea that we had it listen to a classical piece, and it's trying to come up with a new line for that classical piece, right? And then you have the discriminator. What is the discriminator trained with initially? It's trained with the same framework data as the discriminator. So both people start off with the same access to information. Now the main difference between these two groups is that in most GAN spaces, there is visibility to the discriminator, right? It knows the labeling characteristics. It knows the data it's encountering in the initial phase space is true data. When it's originally looking at it, it's going to have sort of a training paradigm, period, in which we're going to effectively initialize somewhat of its capacity to try to identify the initial space. Both of these networks effectively start off with getting a feel for the data. They're then hooked together in such a way as to the discriminator is going to have, now this implies something that's not true, okay? There are not two inputs to the discriminator network. These just apply to the notion that the discriminator input is going to take either a real image or an image that the generator network is attempting to produce that it assumes fits within the distribution space that it has been given. It doesn't know much about what this space looks like, right? It doesn't really understand how it's put together. It's just a big chunk of prior. Effectively, if you were wanting to try to train an image network to produce classical style paintings, you just plug in some giant repository of all paintings done in the, Renaissance, late Renaissance, early realist, surrealism period maybe, okay? Now, what don't you want to do? You don't want to have a lot of surrealism in there along with a lot of realism and a lot of Victorian painting, right? Because those are going to have entirely different motifs about their distributional characteristics. So if you want to create a network that can create really good representations of a specific style, or can create something along the same lines as a specific style, you're going to train it with or expose it to data that is in the distribution of that time period, or if you want to get real specific, for that particular artist. So you might only expose it to or train it on Van Gogh or Monet, right, or Degas, or whoever you're going to put in that other side of it, okay? The corpus of their work, how much information there is really an interesting component of this, because some artists are not as prolific as others, but we may still actually be able to extract some of the relatively useful characteristics from their unique style characteristics and apply it to be able to create an image of that style. So this original attempt here at drawing a number, all right, didn't go so well, right?
It's a scribble.
It looks like a kindergartner that is probably trying to write for the first time, okay? And we can make that approximation in our own mind and say, it did a squiggle. It's like, oh, so cute, gold star, okay? So we say, the discriminator goes up here and says, okay, those are ones that I know. Those are actual numbers, okay? I learned the concept of numbers, right? I know how to do them I can draw them, I can even make them like kind of joined up and stuff like. I'm good at numbers. That's not a number, right? It looks at it and goes, that's not a number. That's not a number. And it goes, you, generator network, you missed the point, okay? The thing you were trying to make is not the thing that you wanted to make. Mm-hmm. And it's going to effectively provide the generator network with the degree to which it thinks it's screwed up, okay? If it says you done did bad, okay, that's like a 0.001 score of numberness. And then the generator network sulks, turns its head, walks back around, goes over back to the distribution, right, and tries again. And it squiggles on the paper, and then it pushes it out the door and hopes that it's getting closer, okay? How does it evaluate that the thing that it's drawing is getting better? This is the teacher and the child, effectively, in a lot of ways. Because the teacher is telling you he's telling you that you made a mistake. Yep. All right? The problem is he didn't tell you the mistake you made. There isn't a specific characteristic that comes in and says, no, you did this part all wrong, like the top curvature is messed up. It's going to require that the system effectively go back in time, look at how it generated it to begin with, and then the error, the relationship between the output, the quality that the discriminator considers the replica to have, will effectively utilize the gradient for the propagation through the system. The confidence of the discriminator with respect to it being 0, 1, fake or real, gets sent back to the generator network, and the generator network propagates that error through its structure in almost the same way we would propagate error in any kind of other fit space. The interesting part is it's kind of a singular number. It's kind of here's a decimalized percentage to which I think it is a good picture. Now the system is going to keep making changes, and it's going to keep updating its approach to the process. It's going to improve incrementally because it knows that its goal is to do what? Minimize the difference between its ability to output an actual realistic image of the type, and we will imply something to that. We will imply that the quality of this generator network to fit to this distribution and to effectively take the internal characteristics of the distribution, learn some internal representation space, right, based upon the distillation of those references, and then be able to expand out a satisfactory example of something that does not exist here, but is the generalization of the entirety of the informational representation space that is contained within it. If you fed it a bunch of pictures of ducks, it would be able to make you a picture of a duck. Okay? This is the component of it that's also interesting. Notice, this network is fanning out. It's going from the embedded representation space that's present relative to the prior, and it's actually expanding the quantity such that it's going to be able to create, for something like this, an image based upon or with the dimensionality of vectorized output representation. Now, some of these systems utilize kernel approximations, much like a convolutional neural network, all right? We call the process through which they kind of travel backwards through the system a diffusion process. The mechanism by which that diffusion process operates is different between different optimizers and regularizers within the space. There's a lot of attempts to create stability. So if you've ever heard the term stable diffusion, that is a specific paradigm that attempts to try to create more stable motion through the generator network space. Once the discriminator network is no longer capable of discriminating between samples provided from the real data space versus samples provided from the fake data space, we discard the discriminator, all right? This can be a mistake in some cases. There's an interesting relationship here, that the discriminator is also learning, and is also learning something of value, and that is the ability to tell the difference, or at least somewhat effectively tell the difference between real samples and fake samples. But when the discriminator stops being able to tell that difference, we kind of consider it effectively useless for our approximation, right? Our forger got so good that our art critic can't tell. However, that art critic may be, for a less sophisticated generator, actually capable of telling the difference between real and fake samples. So in some cases, we may be able to adversarially, all right, that's what this method talks about, the terminology. GAN refers to generative adversarial network. This is the adversary, right? This is the opponent to the generative network's capacity to provide a reasonable output. This idea of pitting two networks against one another and trying to see which one can sort of come out on top is the advantage or is the utility of the system. Now, we know how much cool things it can make, all right? Everybody, at this point in time, I can't even really show you guys anything cool you probably haven't seen already. So I'm just gonna talk about it from a overarching perspective, and that is you can make a squirrel flying a kite on a moon, right, as if you want to, all right? And the system can generalize that concept from descriptor frameworks. Now, those are an extension of a much higher level system, which utilizes transformers to take natural language understanding and then port that into the space of the prior before it diffuses through the generation system. So the stability of that diffusion framework is the avoidance of something that we call hallucination. You guys know what hallucination is? Have you heard it before within neural network space? That is when something is going along just fine, all right? And then it starts making up something that does not make sense. It's actually the situation where the network within the diffusion space, as a result of the intensity of the noise that's being introduced to try to generate variance, some of the bias characteristics in the system can't overcome those noising outcomes. So the noise becomes too strong, or at least with respect is too strong within the system. So we have forward prop systems in which what's happening is actually the values are somewhat exploding forward in the space. The stability metrics come in like normalization and regularization layers to slow the process of the diffusion down so that you don't see exploding characteristics as it's going forward. What do we notice in general? Multiplicative weight systems being run in reverse from node up to node out, large weights that originally would have worked relatively well to incorporate feature space are going to do what in reverse? They're going to blow up the values in that direction. So we're going to have to rein them in. We have to have very specific methodologies for numerically reining those values back in. We're not going to spend a lot of time on that because the fact that those are such complicated elements that they could make up an entire another course, all right? I think you guys have begun to understand that we could seriously keep on this for an amount of time, okay? There's literally probably 5 new models that have come out while we've already been having class, and they're gonna come to prominence and then they're gonna die off before we're even ready to leave, okay? Just like JavaScript frameworks, like they just come and go, like, you know, like the lives of bugs. But this is as such a prolific and such a high frequency space. What is the utility for us? What do we utilize these things for? Okay. First of all, one of the items here is that the generative outcome as produced by the generator system may actually not be that great. Okay? I'm not really sure what that is, but that is not a panda. Okay?
That is terrifying.
It is terrifying.
It's like somebody rotated his head.
It's like, yeah, they
killed
like
it.
completely twisted it, and then, like, where is it?
But
It
think about
feels
this.
weird.
Think about this though. This is an interesting relationship. You guys maybe haven't seen this part of it, okay? So I am showing some of you something you haven't seen previously. Because most of the time, by the time you get a hold of a GAN, it's already had all this problem fixed, right? It's had plenty of time to train and offset and modify. Now, what do we notice about the representation that's available there? What do we notice about the output? It's kind of getting some things right.
Yeah, it's getting a few things, yeah.
I mean, it's a whitish thing with some black spots on it.
I mean, the legs are okay, maybe. I don't know. I mean, it's the head. It's that center face part that they're not getting correct.
That's an interesting relationship.
Yeah.
GANs are occasionally missing something that's relatively important. I showed it to you when we were talking about image segmentation. We're going to implement image segmentation, by the way, as part of our final project. Two things I want to mention. First and foremost, we are not going to have a project 3 officially, but what we're going to do is we're going to have a final project that's going to contain a part A and part B.
Okay.
All right, I'm going to give that to you on Thursday. We're going to walk through it so that you know exactly what's necessary, and you'll have until the end of finals week in order to submit that. So you're going to have about 2 weeks to work on it. It's not crazy, or I'm trying to rein it in, make sure everything's going to be within limitations, but it will require you to think a little bit. All right, so we're going to do some level of transfer learning for pre-trained elements. We're going to create a little bit of our own CNN for image classification, and then you guys are going to have a segmentation network, as well as a GAN. You're just going to train a simple style transfer GAN. Okay, you're going to get a lot of fun with all this stuff. The only thing we're not going to do is variational autoencoders because they can take a long time to train. And as a result, I know all of you worried about your GPU time on your collab, so I'm trying to make sure that I preserve that as much as possible. But some of you might have to either bite the bullet and buy some time, or transition to running some stuff more locally if worse comes to worse. But I want to mention that in case anybody was concerned about not seeing that come out yet. I'm just trying to set what the reasonable expectations are given the time interval that we have remaining. After we got done with the exam, there really wasn't time to do another project and then have the final project. So I said, let's combine the small amount of information I was doing with the final project and have that all as one thing to be able to be toward the end of the semester. All right. What I say in terms of what we're looking at on the screen right here is high-level representation, as we describe it within the CNNs, is carrying the notional aspects of the panda, right? It's learning the basic concept of what's present. White with white fur, black fur, patches, generalized orientation. But if you remember when we talked about segmentation the first time, we looked through and we ran the example with trying to refine the regions of interest. We also looked briefly at the model that attempted to try to capture something like a heat map about which regions of the image were most important with respect to the classification. Remember the cats and dogs classifier that had the face of the animal was considered to be the most necessary in terms of this capture space for the characteristics. Some of these more advanced GAN operations with regard to the stable diffusion systems and the transformer-driven networks are going to actually have an understanding that panda has face, panda face located in generalized space relative to panda body, right? And it is going to, it says, all right, panda body relatively easy, right? Basic structure stuff. Do some image illumination shading. But then, as we get up to the face region, it's going to say, all right, start off with something basic. And then it's actually going to go back and refine it. It's going to refine it and refine it and refine it. It's going to keep attempting to generate regions or areas that are within the highest likelihood of being the descriptive or discernible characteristics of the target class representation. So it's going to say the face of the panda is the most important part. If you will watch this system as it's training, what you'll begin to notice is that the discriminator improves in its quality of output relative to being able to determine that it is or isn't a picture of a panda, as at the same time as the generator gets better at trying to put the places or items in the spaces where they belong, right? Mm-hmm. This is the interesting portion. Technically, the negative samples train the discriminator as well.
Yeah, okay.
It starts to notice how you make things. It gets good at figuring out what your quirks are when you attempt to try to create something unique. There is as much a relationship of the discriminator trying to get into the head of the generator in this particular space. It says, I know what the generator is bad at, right? Now I know what to look for. It's bad at faces, all right? So I'm going to look at the faces. I'm going to look at these regions of high frequency elements. One of the worst places for generator systems, and this is going to persist for a good time, all right? We have not figured out how to solve this problem at a global level, is that the higher frequency spaces where there's the most detail are going to be the real problem, right? They're going to be the real consideration in this space. So while we start off with this particular situation is the generator says, I'm going to attempt to fool you with the discriminated value, or the generated value, right? Discriminator says, I looked at this sample, right? This one is good one, right? And then this one is what? Bad one. We notice it's getting a score of 0.1617 for its quality of pandaness, all right? Now, part of this is actually the ability for the system, maybe in a generator, to be able to produce multiple different kinds of animals. So there can be additional vectors that can be passed off relative to whether or not it's a real image or real target. Now, the discriminator will pass in both samples in sequence, pulling one from the generator and one from the core data set, right, real data set. The order is random. Which one it sees first, whether it's pulling in real or generated, right? Generated real, real generated, generated generated, real generated. It's going to flip around so that it can't cheat and just know which particular set of information it came from. So it's going to try to compare or effectively try to correlate the likelihood of what I say it is with how I would effectively classify that if I were operating as a classifier. But instead of having a classification output in the ends, it's going to topologically compress the output of all the dimensional space at the end of the process to one sigmoidal activation neuron. Okay? Now, you can change that activation type, but usually sigmoidal is the preference because it mirrors softmaxing, right? It mirrors the relationship of understanding the class output for a specific is or is not. Now, since this particular GAN is supplying that information and saying, hey, I'm telling you this is a panda, the system is going to say whether or not that is a real or not real image of a panda. I can also pass it an image of an elephant. It will say it is a real or not real image of an elephant. Now, it is not classifying them like a traditional classifier, but it still understands what the real distributions are of that particular type or that class of particular animal or particular object. So its ability to differentiate between the targeted output class characteristics is embedded from its capacity to look up or recall samples from that distribution space. So it's going to look at a sample of known output, right, relative to a sample of generative output without knowing effectively which is which, and it's going to try to say, are these differentiable from one another? No. If they're not differentiable from one another, then the system has effectively won. Now the differentiability is that it's going to assign a score of likelihood of image belonging to class for each relationship. And once it goes back and does the scoring output, notice something. There's an interesting value here. Notice the picture of the real panda only provides us with a 99.97% chance, all right? So there is a 0.03% chance that isn't actually panda. You know why the reason why I think that is because there's also a tree.
Tree there, yeah, exactly.
Right?
Yeah.
You know, it's obscuring the panda a little bit. But what's the likelihood we're ever going to get to full saturation of that system? Very little. Very little. It probably shouldn't, right? Because it shouldn't establish full confidence, because there are other things that are probably going to be similar to it in both structural genesis and framing and context, right, that may make it difficult to discriminate or differentiate. Maybe a sloth that was in like really dark lighting conditions, right, might look a little bit like a panda. Maybe also a raccoon might also look a little panda-like, right?
Maybe a red panda too, I don't know.
See, that's a different, we're going to differentiate based upon panda color. Right now we're getting into fine granularity. That is a relationship. How many classes are you going to be able to satisfactorily complete for both generation and discrimination before it's going to get hard to be able to tell them apart from one another? If I have to be able to tell regular panda away from red panda, now we have an additional value issue. Look up there with relationship to the original images. Notice the original image has a lot higher white balance, almost up toward titanium, right? But then the image that's generated on the output has a nice green hue to it. So if color intensity and color spectra for the output is also going to matter, now we have another situation which the system is going to have to try to find the balance of the appropriate color for the output. It's going to have to fool the system into trying to approximate what the target values are relative to the global illumination of the space. The discriminator is also going to have to do what? Work overtime to try to determine whether or not the color balancing for the general color grading of the image fits whether or not that would be what a red panda would look like with a green color filter over top of it, right? Now, how do we fix this in some respects? We might run it through some sort of a color normalization filter in order to try to fix some of the color anomalies that the generator doesn't quite understand. But we also notice this generator isn't very good yet. So part of the reason why it's likely throwing a lot of green on the context of panda. Pandas live in places where there's a lot of green, a lot of bamboo around the back of them. So it's going to associate from a high-level representation space the context of where the panda is. Here's another relationship that you guys I think will find interesting. What if I said, build me or draw me a picture of someone cooking? What's going to happen? Where do you think it's going to be, right? And what are the characteristics of the individual in that case?
The location of where they're cooking.
Yeah, what is it going to be? Kitchen, okay. Gender of the individual.
Female.
Okay.
Most likely,
Okay.
I think. if we look at like.
No, you're fine. Settle down. You're
I'm
panicking. You're panicking.
Should I defend my answer? No.
Why? Because all of our advertising and media is described around it. What did we train it with? We trained it with our pop cultural notions of the understanding of where people are doing what activities.
Mm-hmm.
It's Plato's cave, again, all right? Its world is projected on the wall in the back of the cave. It only sees the pictures we decided to teach it, and it only understands the connections between the elements in the world based upon what we chose to allow it to see through its keyhole. This is a problem, because we have the ability to higher order generalize relationships between elements. Let me change the context for you slightly. What happens if the kitchen were the kitchen of a restaurant?
And it's male. Yeah, so that's gonna, yeah.
Context implies inherited characteristic. The reason why the panda is shown around something green behind it is because panda and bamboo go together, because we take pictures of pandas in places where they're around bamboo.
Right.
It's easy to understand that its linkage between generative objects is going to have the same latent innate characteristics of the data set they're trained with. These systems are literally products of their environment. They are forward-driven systems in that perspective. Now, can we fix those inherent latent biases within a system at the moment? Not really.
Unfortunately not, no.
The other consideration is these machines are also required to operate inside of human spaces. We're building them for us to interact with, right? So they should maybe take on some of the same generalized characteristics that a human would understand the world in, and trying to take away those supporting characteristics and treat them as naive. What are we going to end up with? We're going to end up with Mowgli from the Jungle Book, right? Trained by wild animals outside of the scope of human endeavor. We either are going to have to domesticate the things we're creating and make them like us and have them take on some of our traits and characteristics, or we're going to have to be fine with them being and going and thinking their own way about everything from a totally uninformed, unstructured perspective. Now, both of those things are interesting as research objectives, but what are some of the key risks we have here? You guys are aware of what's happening with the GPTs. They're learning from their own output, right? GPTs are just a more advanced version of GAN operations. They were trained to try to approximate the syntactic structure of natural human language. The difference between their generative output is text versus image. Why am I spending a little bit more time talking about image generation? Is because that's probably the primary bifurcation between the discipline of NLP and the discipline of what might be considered deep learning. Most of what would be considered deep learning anecdotally is going to be image processing and generation, video processing and generation, right? Structured visual media. Now, we'll talk a little bit briefly about the idea of transformers in the visual space, but I am mentioning this with respect to the idea that there is a very similar process to a training of another transformer network like the ones we use in GPTs, and they're going to inherit the same latent bias characteristics that we're getting from a lot of these other training systems, just deciding what is going to be what we consider to be real, right? What we say is real becomes the constraint of the natural universe that this system inherits. It will not be able to go out and understand the world in a different way than what we've already prepackaged it with. Here's another problem. What happens if we did allow it to be embodied? What happens if we let it go around the world in its own little Tesla bot frame and walk around learning things? We have to be running both the generator and the discriminator constantly at the same time, right? We're not deploying the networks. They're going to have to run live. They're literally going to have to be outputting at the same time they're trying to discriminate their own output. Self-reinforcing operations. What do we notice about as we increase the number of epochs most of the trained systems we deal with have? They overfit, right? We're going to have to introduce some new tools and new ways to train these systems to stop them from converging to unrealistic outputs, to stop them from saturating, to allow them to continue to learn and adapt as the corpus of information is being expanded as they're experiencing the world effectively in real time, right? I'm going to expose you to a terminology here that I'm not going to spend a ton of time on, and that is the notion of what's called liquid networks. MIT has been working on them for a little while, probably the last 1.5 to 2 years, and these are networks that never stop training. When you throw a new sample through them, they update their weights, all right? And they will never quit. They have special mechanisms in them that attempt to try to stop them from effectively overfitting to specific sample distributions, and they're able to continue operating as a trained output with some form of controlled propagation to be able to advance and improve their sentiment. There was a previous set of disciplines that was revolving around the notion of artificial neural networks, which we talked about as adaptive systems. Adaptive systems also had that same framework in which they were intended to utilize their own, some portions of their own output as a relationship to their next state updates, all right? But liquid networks are a very interesting topic. If you're really wanting to sort of go into some edge space stuff, you want to do some research-driven stuff. There's 2 spaces in sort of the next generations of active learning systems, and I'll try to introduce as much as we have. We have this lecture and 3 more, excuse me. And we're gonna go right up to the end with information because we don't have a final, so there's gonna be no review. But I'll try to keep engaging in some stuff like this, all right? But one of the other topics that's sort of coming into the space is what's called neuromorphics. Neuromorphics are mechanisms for ANNs that attempt to try to make their performance more like biological structures. So we change the way they activate in order to be able to improve their performance. Neuromorphics and liquid networks are actually being thought of or being discussed for potential types of implementations of constantly evolving GANs, okay? To be able to try to figure out a way to keep a GAN constantly improving, constantly learning, constantly generating something new. These are always my favorite slides, all right? Anytime I throw up an equation that has this level of complexity to it, what are we really looking at here? The initial case is looking at some gradient characteristic with respect to the distribution of sample characteristics, right? And is introducing some noising characteristics. Why do I need noise? We talked about this once. Why do I need noise to generate a sample from the generator? Yeah.
So in the real image, there are a lot of noise that's occurring. So if we add some noises, it can look natural, more to it. It's one of the reasons it can.
Okay, so you're right. You got about 80% of the way there. There's one little piece missing. Anybody else want to give a shot at it? Yes, sir.
Would it be because when you add noise to it, it'll be harder for it to identify what it is, and then whenever you actually run the model, it's a little easier for it to figure it out?
That's on the data augmentation side, and that's correct. You can enhance the output capacity and make the discriminator more robust by adding noise to the base samples. All right, so that would be one mechanism you could do it with. Noise does stop the system from overfitting a little bit.
Yeah, I missed it.
What's
yes.
Say again?
Why do overfitting?
So avoid overfitting from the input side, right? So when we're taking their source data, we noise it. You guys are actually not there yet.
Yeah.
You guys aren't there yet. What is the size of the latent dimensional space? It's less than the output space target, right?
Yeah.
It's compressed. I need the noise to initialize the gradients of the generative outputs, right? Previously, we were calculating the outputs from what? Activation functions. Now we're going through activation functions out to distributors rather than integrators, out through weighted frameworks. The noise actually makes the output of that system random. It's the priming the pump. It's starting the initial process. It's the reactant necessary to expand. It's the air pump that puts the noise back in, right? It puts the space back between the features that the original latent space dimensional reduction accomplished. So noise is random. We want random outputs such that whenever we ask it to give us a new picture of something, it gives us a new picture that it hasn't made before. We don't want to get the same output every time. If we fix the seed of the noise we were adding, what do we get? We get the same image over and over again. So the idea of the randomization of the noise is that this is when you're inputting it through the training space for something like an auto encoder, what happens to it? That process is a stochastic methodology. What happens when you run it the backwards direction? It's a forward process. It's known weight values, right? It's just multiply by matrix. So the noise initialization vector is actually in there to tell what values are going to be propagated through the system relative to whatever class we've selected to have that particular target present in the image. So the relationship here is that the random noise that's being sent in is a vector, Gaussian noise vector, that's put into what would effectively normally be the output, right? Kind of the classification layer. So previously we were watching it take it to the embedding layer, right? Now we're flipping it the opposite direction, taking the embedding layer and making it try to generate a new sample. What do you start with? You know what class you want, that's only one value in that vector. The remaining values in that vector are going to have to be just random seed values. They're going to have to be random numbers. So the diffusion process then is going to take that random thing and try to create a version of an image that corresponds to however that initial random matrix was constructed for the input. That's the really weird part of it. It's the part that makes the outputs interesting because we get something new every time, but what are we really getting? We're really getting just a truckload of dice being dumped out of the back of a pickup truck, right? And then watching how all the dice come out and going, all right, that's the initialization framework for the system. Okay, let's look at what we do with these for the most part. Applications in GAN space.
Ugh, okay.
So feature additive characteristics or alternative pose variation. Now some of these aren't very pretty. Some of these are almost a little, I think maybe I need to find a little bit newer systems, but
Oh boy.
yeah, so what do we start off with? Well, we start off with original base image. We characterize what's present within the base image, and then we look at where it might already set with respect to the distribution. So in this particular case, we have someone smiling, someone neutral, right? We have male and female images from smiling, neutral, female images, and then neutral male image. Now this neutral male image is what? It's a composite generative output that is hallucinating a ton, right? The stability framework of its diffusion means that it's not taking into consideration the context of the value around it. If you think it's bad now, it's going to be worse when I zoom in, okay? Notice what's happening with the picture of the man.
Stretching out?
It's stretching? I mean,
Pose variation. This side of the image looks like it's effectively looking at him from the side. Also notice, no agreement between the eye color, no agreement between pose variation relative to where the eyes are looking. One is canted in on the left-hand side and the other is straight, okay? He's got a 5 o'clock shadow on the left-hand side and relatively clean shaven on the right.
Yeah.
There's a lot of stuff going on with this image that's just not lining up with our sensibilities because we as humans are looking at the whole of the structure. If the initial seed is just random, then it's going to do what? Mr. Potato Head. That's what this is, okay? That is just, it's just recombining known characteristics of elements from the distribution of all the samples it was originally trained with. Huh. So, let's imagine that you have a bunch of images. And you wanted to do something like what's happening up top. You wanted to add sunglasses to them. That's a reasonably good application, right? Detect where the face is, the eyes are, right? Pop in and says sunglasses. You guys have seen that they have some apps now where you can try on glasses and try on sunglasses, right? Using face tracking. Now those are a combination between elements. The GAN sample space, the output GAN sample space is informed by a model that localizes, segments where the elements of your face are, right? So you have a segmentation model feeding in where your eyes are, where your eye band is, ears are, nose, etc., where pose positioning. Feeds that in as a vector to the GAN to be able to stabilize the output such that it's not just making up everything from whole cloth, right? It's not totally random. We're not totally randomized because we're not totally randomizing position, location, and scale of the target object. We want it to have a specific scale, we want it to be positioned in the appropriate location, right? And we want it to have the correct orientational characteristics. So by having some information supplied by external information about the target space that it's going to go in, the in-painting, the ability to add the information over top of the existing data, is going to be fusing new generative output over top of the existing image input space. So I'm going to put the image in, I'm going to say which area of the image I want to modify, and then I'm going to feed the system forward until the output is effectively the same as the input plus whatever I decided to add to it. Now, This image is up here, poor stability in a lot of respects. These images down here, also terrible stability with a lot of respects. What also do we notice with respect to where we are now? So much better than where we were even when these slides were made. These slides were made by LeCun, I believe, in 18, all right? So in the last 6 years, this technology has developed this far. To the point where I know today, if you guys have ever seen the website, this person doesn't exist, right? Have you ever seen it?
No.
Okay, hold on, I'm gonna look it up.
Oh, yeah, no, never mind. Yeah, I remember.
Yep.
It was, yeah. Wow. So close. Like
This is
you're-
GAN.
It's like, I can't even tell if it's, ugh, okay.
Now, the only thing it can do is faces. All right, that's it. That's it. It's confined to this, it's confined to this distribution space. What's one of the other things we notice about it as far as distribution space characteristics go?
It's really good.
Oh, it's amazing.
Yeah, it's not even, well, I mean,
It's
there
not,
might be some
oh
parts,
my
there
god.
might
It's
be
the
some
shadows.
small,
Also so precise.
there must be some
going
small,
on?
very, very small that we can't see, like some dwarfed area.
Are all the backgrounds?
I'm not really sure why we have,
Except
I'm not really
this
sure why
one.
we have these advertisements on campus, but whatever.
Except this one,
this
the arm
side of the-
is
it's-
not quite right.
Like you said,
on the
it's the
left
face,
side.
not
Look
the.
close at the symmetry characteristics in some of the spaces. The chin is not quite appropriately centered. The ears have spatial asymmetry
Yes.
beyond what is traditionally considered in the norm space. The reason why is the moment a GAN leaves a region. Now this is a specialized type of GAN. This is one that has transformer characteristics and side memory aspect to it. It's a stable diffusion framework. When it leaves its space and it moves to a new area, it's only keeping track of the context of what's around it to inform it as to what it should draw next within that space. So especially at the higher resolution space, it can't keep track of all the feature characteristics for the whole frame simultaneously. So if you've ever noticed within generated image frameworks, you can watch a tree limb through a window frame and watch as it goes from one pane to the next pane, and notice that there's no agreement between those. It doesn't understand the concept of flow and continuity through occlusion. So as soon as it loses track of what it was doing and moves into the next pane, it's not utilizing the previous pane because it does not understand that there is a continuous concrete world out behind that. It's treating it just like it would a picture or painting or any other structure, right? So like I said, this is what they look like now in comparison to those horrible aberrations that we saw earlier, those nightmare fuel-inducing structures like these things, okay? So I have to subject you to this. So the reason why I have to subject you to this is because in order to understand where we're at, in order to understand what the limitations are, there's another thing that I want you to take into consideration. If I were to attempt to try to use a GAN in order to present or create more samples for a data set, what are the risks? Could I take the images from this person does not exist and utilize them to train a facial recognition system? Would that be a good idea?
No.
Why? I seriously want you guys to think about that problem. I'm going to talk to you about it again whenever we get a little bit further down the line, but I want to talk about this one real quick. Now, this one's cool. This one's really neat, and I want to talk to you about this because there are actually a couple very high-level representations of this technology utilized in several different places. One, image upscaling is able to take images from past cameras or whatever else and upscale them such that the texture characteristics of the system can be far beyond the scope of what was originally present. Now we notice that if we have just the bicubic upscale operation, that's relatively poor. That might be the standard one that we would utilize. We also have the SRCNN, right? That's the segmentation and localized rationalization recurrent convolutional network, in which as I'm moving through the system, what am I doing? I'm feeding back the context of where I've moved so far in order to be able to tell what to generate next. Now, what am I actually describing by this concept of super resolution? What do I mean by super resolution? I'm talking about taking an image at some original scale, pixelated image, and I want to blow it up such that I retain the feature characteristics as well as actually enhance some of the feature characteristics given known parameters about the standardized distribution of photographs. These systems don't just have an understanding of one representation space. The ones that work incredibly well are cheating and generalizing based upon billions of photographic images. There is another application of this technology. Notice what happens with EnhanceNet down here. Incredible texture transfer resolution, right? But the original resolution space, okay, a little bit off.
Yeah.
SRGAN and ERGAN, we're retaining, you see a little ringing in this one. You see a little ringing because you see a little resonance. But that's a common factor with generative images. We talked about that a little earlier on in the class. So ringing is because the kernels they're utilizing. This ESRGAN is, so this is going to be SNR characteristics for the system, right? Signal to noise ratio aspects. The improvement of the signal gain structure relative to the noise structure is always going to be the value or utility of the upscaling. Now, how they actually work this is they downsample the original image, and then they attempt to get the system to reconstruct the previous high resolution image. Does anybody know what one of the most common modern applications for this technology is? Anybody play games? Any of you have an NVIDIA graphics card?
Yes.
Have you seen the option that says DLSS?
Yes.
That is deep learning super sampling. So I can actually create a system that says, I don't need you to actually render it at full resolution. You can render it half resolution, and I'll just guess at what the pixels in between should be. If I have a good enough understanding of the context of what's present, it actually takes less computing power to upscale the original image than it would have to generate it at the targeted resolution. So you can, instead of rendering something at 2K, you can render something around 720p or 800, 900p, and then use an upscaling GAN system to take that original input space and hallucinate or fill in the blanks of what would be present based upon the generalized capacity. Guess what it can do? It can fool you into thinking that that's basically the same as it would have had rendered at the original resolution. This is a really interesting technique because it's saving computing power, because the construction of the GAN, the generator output, is actually lighter than the construction of the rendering and image pipeline, right? So the image rendering pipeline, the RTX, ray tracing structures, and other polygon rendering frameworks. So this is something that's actively being utilized right now. And from the perspective of saying, one of the goals is to try to drive up realism. Realism would be what? Increasing the frame rates. Because our eyes don't operate at frame rates. We need higher frame rates to simulate realistic world space. So driving up frame rates by reducing the computational time by off-sourcing or handing off each framed image into a feed-forward process that approximates what would have happened had we actually rendered it at 2K, even though we only needed to render it at roughly half the resolution. Pretty cool, right? Okay. Style transfer is one of the last GAN applications we'll talk about. You guys are all pretty familiar with this, and that is that if I have some image space input, and I have some generalized understanding of what the target space is, I can create a map between these two elements, be able to notice common features between those. So I say that the input up in the top left-hand corner, right? This is the zebra again, all right? That's to zebrify whatever I'm looking at.
Oh my god.
It's a zebrification algorithm, okay?
Oh no.
Yeah, all right. So we're gonna train one of these. I'm not sure what we're gonna train it on or what the goal is gonna be, but your objective is going to be to try to create something funny with a series of sample images for some kind of style transfer
I love
space.
it.
All right, yeah, it's an interesting application. Notice here, this one down here, the only thing it's really doing is transferring color, or at least transferring somewhat color space, right? But what it's actually doing is it's attempting to try to turn apples into oranges. So what do we always say about this? This is something you shouldn't do, all right? Don't compare apples and oranges.
Exactly, I was about to say, like, that phrase
It's
is
breaking the
wrong.
rules. Yes, please.
Is this image to image, or does it need a text description that's doing this?
It's image to image. There isn't really any, like, we're not really providing any vectors for the support operation. What if we were providing a vector for the operation for a broader style GAN transfer system, we just have to say, utilizing the input image, attempt to try and restyle it or provide a new style with the target style. Say, convert the fruit in this image to oranges. So it would then have to segment and understand structurally what are the elements in the image space or the fruits, right? And then attempt to try to convert them over to oranges. We notice here, it's not attempting really strongly, at least it doesn't seem to be, to try to convert the leaves into oranges, because the leaves aren't orange, but maybe. It doesn't really seem to be able to cleanly differentiate between the fruits in those cases.
So
Yes.
the set of real information that's going into the discriminator network would be, in this case, like the oranges. And then it's using like the generated output would be the.
Correct. The oranges would be the goal, right? The goal would be to try to say, create an image that contains oranges. And then the transfer operation would be similar to the one that we did with the idea of the in-painting, where we're going to supply, instead of a random array, we said that if we don't want a true image to be naively generated, that's an image without any presuppositions, we could just feed in random noise. But instead, the style transfer operation feeds in a known array of elements and then gets the system to transform that array of elements into a orange impersonation, right, in that particular process. However, once we're in deployment operations of these structures, there's no longer a discriminator. Right? The discriminator has been taken away. We're going to become the discriminator. We're going to be the ones that determine whether or not the image that it created as a result of the process is actually a good one. That's one of the things that I want to imply here above probably everything else that's a take-home from my talk about this. These tools are not going to replace human artists. They're not going to replace photo editing. They're not going to replace any of that stuff, not anywhere in the near future. Right? They're getting better, yes, and they're getting relatively amazing at what they can do. But there's one last thing that they can't do. They have no idea whether or not what they made looks good. Right? They don't really have, the discriminator doesn't do anything more than just tell whether or not the output is within the constraints of the desired characteristics, the probability distribution of the class of interest. It doesn't have that sort of aesthetic characteristic to see whether or not it appeals to people. So at the end of the day, we can still create these tools. We can still find high utility for these tools, but we're going to need people to be able to employ them and use them in order to create appealing outputs to people. These could be great enhancements for creators and generators and all these other things, but at the end of the day, it kind of needs us to be able to have both the reason to do what it's doing and some sort of the impetus to do that, but it's also from the perspective of someone to come in and say, yeah, that one's a good one, right? Or that actually looks like a zebra, right? Those considerations above and beyond just the attempt to try to minimize gradients. Those are the key factors, all right? Anybody have any questions? All right, well, I'll see you guys on Thursday. There was a talk upstairs that is related to biomedical engineering. The chancellor is giving a talk. It's 6 o'clock, I believe it starts, and
6:44.
6:45? I think it's 6 o'clock to 7 something.
Oh,
I think it's 6 to 7:15. There's been flyers around the outside, but if you guys are interested in anything that has to do with like biomedical engineering or seeing what that program is gonna be like, obviously just encourage you to attend. Another thing is constructive criticism of this course, both my implementation and elements that might be able to improve my approach for others. Open. I'd appreciate it if you give me a review through the RU path. Okay. They told me the other day that nobody's given me a review yet. I'm assuming that's because you guys don't know what your grades are going to be. But it is open till the end of the semester. All right. So if that's what you're holding out for, okay, it's not really what the point is, but at the same time, I understand. Okay. We'll talk to you soon. Yeah.